Greetings, physics enthusiasts. Welcome to AP Physics 2, Unit 5, the first lesson. In Unit 5, we are going to talk about magnetism. And so in this introductory video, I'm going to talk about magnets two different ways. I'm going to go over what you probably know about magnets that you've seen around you. And then I'm going to talk about more physicsy formal magnetism. So we'll start with the stuff that you see around you. And around you, you have seen magnets. And you know that magnets exert forces on each other. So this is a picture of a magnet. And then here's a picture of another magnet. And what you've seen is magnets can exert forces on each other without touching each other. Forces without contact. Now in physics, that has a very fancy phrase. Action at a distance. But if you remember that the word action in physics is a synonym for force. Action doesn't mean an occurrence or an event. No, action means force. So in Newton's third law, which says every action has an equal and opposite reaction. That's not saying, oh yeah, stuff causes other stuff. No, every force has an equal and opposite reforce. So this is a force at a distance, and at a distance means not touching. And that's kind of magic, right? That, you know, if you watch TV shows about magic stuff, one of the main ways magic happens is I can push that thing without touching that thing, or I can pull that thing without touching that thing. So when I was a kid, I had a little box of magnets. And one of my favorite things to do was to sit underneath a tabletop. And I would put one of the magnets on top of the table, and then I would go underneath the table, and I would have another magnet. And by moving the magnet under the table, I could make the magnet on top of the table move. And I just thought that was fascinating because, although I didn't know the phrase, I was watching action at a distance. I was watching pushing without touching. Now, this magnet can push this magnet away. This magnet can also pull this magnet in. And it has to do with this, the fact that magnets have different sides. And the way we name the different sides of the magnets is we call one side the north side and the other side the south side. And so if these magnets are lined up so that their norths are both on the left and their souths are both on the right, then these magnets will attract each other, or this one will pull this one left, and this one will pull this one right. That use of the for sentence is so much more meaningful than they attract each other. This one pushes this one left. This one pushes this one right. And that's because these things, north and south, are opposites. And we say opposites attract. Attract. And likes repel. So if instead of setting them that way, if I still had this one, north on the left, south on the right, but I had this one, north on the right, south on the left, these two souths would repel. So this magnet would push this magnet right, and this magnet would push this magnet left. And I think you're aware of that, but that's what happens. So two magnets can exert forces on each other, either attractive or repulsive forces. It's very important. This N looks like a W. N. It's important to know that we name the sides of the magnet north and south. They are not there. This has nothing to do with there being positive charge or negative charge on one side. I just went to a meeting recently where a bunch of science teachers were talking about the positive end of a magnet and the negative end of a magnet. Oh my gosh, don't ever say that. Magnets have north ends and south ends. Not positive and negative. Now, there is something to do with charge that in the second part of the talk I will discuss, but not now. So magnets, north end, south end, action at a distance. And they're very fun. You can buy magnets online. You can buy magnets at science stores. You can buy magnets at toy stores. You can buy magnets at souvenir shops to stick on your refrigerator. I'm pressing pause. And I unpaused. I wonder what I was talking about. Looks like we were talking about magnets. Okay, so I think we were probably done with talking about those. Now, another way we talk about magnetism in our world around us is we talk about our planet Earth. And we talk about the planet Earth having a North Pole and a South Pole and an equator. So if you know, you are here, because we're in California, Los Angeles, that's probably around there. So I've just defined this as the Northern Hemisphere. So this is the North Pole, you know, up here in Canada. And this is the South Pole down there in Antarctica. So there's the South Pole, and there's the North Pole. And then people have these little things that are called compasses, which has a little needle here. And it has a north end and a south end. And here's a phrase that's helpful. The north end of a compass points. What direction does the north end of a compass point? Well, the whole point of a compass is it says that way is north. So the north end of a compass points north. So feel free to say that and memorize it. But that means that the north end points north because it's attracted up there to the north, which means the Earth really behaves as if it has a big old bar magnet inside of it. The challenging thing is that this big old bar magnet inside the Earth, I know you think I made a mistake because I was talking and writing at the same time, and I do that, but not here. There is a magnetic South Pole up at the North Pole because the north end of a magnet is attracted to the south end of that magnet. So the compass, the north end points north, but north and south are attracted to each other. So Earth behaves as if inside of it there is a big old bar magnet oriented that way. Well, that's fascinating. Maybe you already knew that. Maybe that's unexpected. Now, this is one way of looking at Earth from the side. Let's look at Earth from above. So here's a picture of Earth again. But bam, that's the North Pole. We're looking from above. And this is the equator going around. So we can't see any of the southern hemisphere. We can't see Australia. We can't see South Africa. We can't see Argentina. All we can see is all of the northern hemisphere. Now, the reason I'm showing you this is I'm going to call this GN for geographic north. And when the Earth spins on its axis, this would be the axis of Earth. Now, the magnetic north is pretty close to there, but it's actually not in exactly the same place. Geographic north and magnetic north are not in exactly the same place. Geographic north, again, as Earth spins on its axis, those would be the places that rotate, but they don't go in a circle, the North Pole and the South Pole. Geographic north. Magnetic north is where the north end of that magnet, or actually the south end of that magnet, would be. They're not quite the same. And just for fun, you know, this could be interesting, or if you ever go camping, this becomes super important. Because when you go backpacking and you use your compass to follow the map, well, your compass is going to point at magnetic north. But your map is drawn based on geographic north. So there's a difference. And we measure that difference as an angle. But the angle would be a different amount in different places. What if you're here? Well, they both point the same direction. So the angle theta would equal 0. Here, that angle is not 0. Do you see, as I get closer to the equator, that angle would get smaller. As I move higher and higher in latitude, that angle would get bigger. So theta could range, from 0 all the way up to 180 degrees. This angle that is the difference between where geographic and magnetic north is called declination. And it's not really a part of this course, but I just think it's a really fun word. And it's a neat idea that geographic and magnetic north are not quite in the same place. Also, surrounding Earth, because there's this big bar magnet on the inside, there is a magnetic field. And the magnetic field is these big loops. And as you can see, these magnetic fields form loops. And as you can see, at some places on Earth, they're parallel to the ground. And in other places on Earth, they're not parallel. And so the measure of the angle between horizontal and the magnetic field, which is 0 degrees here and can be as much as 90 degrees here, that's called magnetic dip, D-I-P. And that's just a fun word like declination. And there are ways of measuring how Earth's field is in relation to Earth itself. Now, as you remember, field lines have a direction. So our gravitational field lines point down here near Earth. Our electric field lines point in the direction that a positive charge would get pushed. And then our magnetic field lines also have a direction. And the direction of the magnetic field lines is this. So very positive and uplifting. They point up out here, and then they point down going through the center of the Earth. And the direction of the magnetic field lines will become important later. Okay. That's all I need to tell you about the first way we're talking about magnetism, how we experience it around us in the world, or what may be some of your background knowledge. But now we're going to talk about physics in terms of fields. And of course, we're interested in two things regarding a field. We're interested in the source of that field, what created it. Like Earth creates the gravitational field, or I create a gravitational field around me, or charged particles, protons and electrons, create electric fields. What is the source of this magnetic field? There's one question. And then what does that field exert forces on? So what makes the field, and then what does the field push? So what I'd like to do is start with a review of the fields we already know, gravitational fields and electric fields. All matter creates around itself, creates a gravitational field. So Earth creates around itself a gravitational field that points toward Earth. I create around me a gravitational field that points toward me. This pen creates around itself a gravitational field that points toward the pen. So all matter does that. And gravitational fields push all matter. Not just charged matter, all matter in the direction of the field. In other words, the direction that the field points. So here's an example of Earth. and the field points toward Earth, and any matter in that field would get pushed the direction that the field points. Now, electric fields are a little different. Charged matter creates around itself an electric field. So would a neutron create an electric field? No, because it's not charged. A proton would create an electric field, an electron would create an electric field. Would a magnesium atom, which is neutral, create an electric field? No. Would a magnesium ion, which is charged, create an electric field? Yes. So the source of gravitational fields, matter. The source of electric fields, charged matter. And electric fields exert forces or push all charged matter, but they don't push on neutral matter. So an electric field, if there's an electric field like this, if I put charged matter in here, the field would push it. There's my E for electric field, little G for gravitational field, which should be in black because this picture's in black. So matter creates gravitational fields, and gravitational fields push all matter. Charged matter create electric fields, and electric fields only push on charged matter, not on neutral matter. And then the thing is slightly more challenging about electric fields is that electric fields push positively charged matter in the direction of the field, and electric fields push negatively charged matter the other direction, opposite the direction of the electric field. Whereas gravitational fields push all matter the same direction, in the direction of the field. Now, magnetic fields, which we'll have in yet another color, are even more complicated. Moving charged matter creates a, magnetic field. So what creates a gravitational field? Matter. What creates an electric field? Charged matter. And what creates a magnetic field? Moving charged matter. Moving charged matter creates a magnetic field. And magnetic fields exert forces or push moving charged matter. So if I have a magnetic field, which I'm going to label letter B because we use capital B for magnetic field. Sorry, we don't use M for magnetic, we use B. So if I have a magnetic field here, would the magnetic field push all matter? No. Would it push all charged matter? No. It's going to push moving charged matter because it was created by moving charged matter. So we will elaborate on just how it is that moving charged matter creates the field and how it is that moving charged matter gets pushed by the field later on. But that is what magnetism is. So there we go. Let's draw this a little bit bigger now. But this page, this is worth pressing pause and copying down. Really important. Make sure you can say that and make sure you understand it. Now I'm going to elaborate on it a little bit more. I'm going to draw my B field, which is my magnetic field. And remember how gravitational fields were easy. They push all matter the same direction. And electric fields were a little more complicated because not only did they push charged matter, but they pushed positively charged matter in the direction of the field and negatively charged matter opposite the direction of the field. Well, it turns out that magnetic fields, capital B for magnetic fields push moving charged matter, but they don't push moving charged matter in the direction of the field. In fact, they push moving charged matter only if the moving charged matter is moving in a specific direction, if it's moving perpendicular to the field. So let's say I have a positive charge and it's moving this way. So this is V, its velocity vector. If the charged matter moves perpendicular to the field pushes it. If the charged matter moves in the direction of the field or opposite the direction of the field, the magnetic field does not exert a magnetic force. It does not push this charged matter. So the motion has to be perpendicular to the direction of the field. And then it's really fun. You're like, well, what direction does the field push the moving charged matter? The force and the field and the velocity, those three things, the force, the field, and the velocity. Can you see how I'm doing this with my hand? And I'm putting them in a shape like an X and a Y and a Z axis. The phrase for that is mutually orthogonal. Orthogonal. Orthogonal just means perpendicular. So in other words, the field, the velocity, and the force, well, there's two directions that are perpendicular to both these green arrows and this black arrow. Into the page and out of the page. So the force exerted by the field is not in the direction of the field. It's not opposite the direction of the field. It's perpendicular to the field and perpendicular to the velocity. And the way we do that is we use our right hand. Don't use your left hand. So set your pencil down if you're right-handed and use your right hand. And we're going to go V, punch in the direction of the velocity. And then stick your fingers out. So V, B. And so what you're going to do is, while keeping your arm punching in the direction of the velocity, I can keep my arm punching that direction while I rotate. And I'm going to rotate like this until my fingers are pushing in the direction of B. So here, look, I'm going V, V, and then I stick my fingers down, B. But that's not the right direction. So while keeping my arm in the direction of the velocity, I have to rotate. Oh, there's B. Now my fingers are pointing in the direction of the magnetic field. V, B, I make a sound effect for twist. And then my thumb, which you can't see, but my thumb sticks out now, and that my thumb is F. V, B, F. And you'll see those three things are mutually orthogonal. This way, and this way are mutually orthogonal. So here in the picture, it's V, B, F. My thumb is pointing into the page. So this field will push this positively charged particle that way down into the page. And the way we draw into the page is with a little X. If we were pushing out of the page, for example, if this were a negatively charged particle, it would get pushed the other way. So I do V, B, F, except it's negative. So a negatively charged particle would get pushed out of the page, which we draw like this. X means into the page, dot means out of the page. This is like looking at an arrow when it's coming toward you. This is like looking at an arrow with those little feathers as it goes away from you. So practice with the VBF thing and with the phrase mutually orthogonal. All right, so now you might also be wondering, let's see, yeah, really close. What if the magnetic field points this way? And I've got a particle that's not moving this way, which would experience no force. The field would not push a charged particle if the charged particle moves these ways. Remember, the charged particle has to move perpendicular to the field. What if my charged particle, positively charged particle, were moving this way? Well, that's not parallel and it's not perpendicular, it's diagonal. So what I would do is I would take this velocity and I would break it into components. And I would call this V parallel because it's parallel to the field. And I would call this V perpendicular. And I would just throw this parallel part away because it doesn't contribute to the force. And this velocity is what I would use to determine the size of the force exerted by the B magnetic field. Now you might be wondering, how hard does the field push the moving charged particle? F sub B. This is the magnetic, B for magnetic, force. B is the magnetic field. F sub B is the magnetic force. And the force is directly proportional to the magnetic field. Stronger field, stronger force. It also has to do with the amount of charge. More charge moving would experience a greater force, would get pushed harder by the field. And of course, if it's this motion that has to do with the force, that velocity also matters. So QVB, there is your super important equation. Magnetic force equals QVB. Now, there's two ways I could modify that. I could say magnetic force equals QV perpendicular, because it's really only this part that matters, QVB. That's great. Or another way of saying V perpendicular is QV times the sine of theta times B. So I'm just taking, if this is theta, V sine theta is this. V perpendicular is V sine theta. So sometimes that's written as FB equals QVB sine theta. So the force is QVB if the velocity is perpendicular. If the velocity is not perpendicular, I take the perpendicular component, which is V sine theta. So that's an equation worth memorizing, QVB sine theta. And you'll get used to saying QVB, QVB, QVB. And then using QVB, magnetic force equals QVB. Well, let's look at the units. What is the unit for magnetic field? We haven't talked about that. Well, B is F sub B over QV. So the unit for B, when I put it inside these brackets, it means the unit for. The unit for B is the unit for force, newtons, divided by the unit for charge, coulomb, divided by the unit for velocity, meters per second. So there you have it. The unit for magnetic field is newtons per coulomb meter per second. The unit for magnetic field is newtons per coulomb meter per second. Cool stuff. Now, of course, the unit for force, the unit for magnetic force is newtons. The unit for electric force is newtons. The unit for gravitational force is newtons. The unit for all forces is newtons. But the unit for magnetic field is newtons per coulomb meter per second. Newtons per coulomb meter per second. The unit for magnetic field. The unit for electric field was newtons per coulomb. And the unit for gravitational field was newtons per kilogram. These are the units for the field. Gravitational field's unit, newtons per kilogram. Electric field's unit, Newton per coulomb. Magnetic field unit, newtons per coulomb meter per second. But the unit for these three forces is always just Newton. And a lot of times we don't have this memorized. You can figure it out just by looking at that equation right there. And that is my introduction to magnetism. I hope you have some things that you wonder, and I'm looking forward to answering your questions when I see you. Have a great day. Be careful. Don't break the laws of physics.